shared, right? Yeah. So today I'm going to be talking about um, grid combo, which is combinatorics on a grid. And, you know, usually the type of grids that we're talking about are like square grids with like a bunch of unit squares here. I'll like draw one. I'll draw one on this right side. So like something like this. But like there's really no difference. Like the type of grid that you're operating on. A lot of the time, the techniques that you're using are the same. And honestly, after you get more experience, you'll realize that a bunch of grid combo problems actually use the same techniques as non-grid combo problems. So today I put together like a problem set that will hopefully give all of you a little bit of intuition as to how to approach grid combo. For those of you with like a strong combinatorics background, you'll find that a lot of the techniques we'll be using today are actually quite similar to the techniques that we use in other types of combinatorics problems too. So yeah, but there are some specific techniques just to do grid combo, and we'll also be seeing some of that today. So yeah, since some of you joined a little bit late today, uh, I'll give all of you a little bit more time to look at the problems. Make sure that you've seen at least, I think, the first few, right? And give an honest attempt on them so that when we discuss it, you'll have a better sense of what uh, I'm doing. So yeah, I'll give you guys like, I don't know, 15 more minutes. Is that good? Or is that too much? All right, yeah. Then I guess I'll yeah, then maybe until like 11:05, I'll give you guys a little bit of time to read through them and then we'll get started on the discussion.
Could you maybe in the meanwhile show the problems because this recording will be uploaded where the problems will not be posted along with it. I mean, it can be posted, but not many people will see. So I think
I just-
if you can show it right now, yeah.
All right, yeah. So here.
Do you have the PDF handy? Or oh yeah, there you go. Yeah.
Yeah.
Could you zoom in a bit?
Yeah, so I would recommend definitely looking at the first three and then maybe also looking at four and five if you have time. But
Mm.
also the last few are interesting, and if we have time, we'll get there.
Yep. Could you zoom in a bit? Yeah, a bit more. I think. Yeah, that's fine. That's perfectly fine. Yeah. Thank you.
All right. I guess I'll start talking about the problems a little bit early, um, just to make sure we can get through a good amount of problems. All right. So, does anyone have any problems that they found interesting and want me to talk about? All right. If not, then I'll start with problem two, because it's a good introductory problem to demonstrate how, techniques, like general techniques, can be used to solve combinatorics problems. Okay. So has I'm assuming everyone has read the problem. So we have an n by n squared grid. I have to move the whiteboard. Yeah, so I'm just going to use the one I made previously, the 4 by 4. So we have an n by n squared grid, and we color some non-empty subset of the grid pink, right? I'm just going to color it black, but yeah. So let's look at the example where I colored this square, right? And we're asked to show that you can divide the square into rectangles along cell borders such that each rectangle contains exactly one pink cell. So, when there's one, uh, no, yeah. So when there's exactly one pink cell, what can we do? This is quite easy, so any of you can like put the answer in the chat. But when there's exactly one pink cell, what division do we do? Yeah, so we just take the entire thing. Pretty easy. But what happens when we color in another pink cell? What do you think we could do here? Well, okay, so, you know, yeah, we can just divide it in half along this line right here. So this suggests a pretty simple um, generalization, right? For example, let's say we have this configuration. What we can do is we can divide it along the grid lines, right? And then we can in like the already existing divisions where there are more than one pink cell, we can further divide those in half or something like this, right? And so to formalize this, we could use induction, right? I'm not going to do that here, but this is meant to be a pretty easy problem. But it's a good demonstration of how, we can use induction in combinatorics problems, uh, induction is quite a general technique. So here I'm just kind of demonstrating that, you don't want to forget your general basic techniques as they can be very, very useful in these types of grid combo questions. All right. Does anyone have any questions about that? No questions? All right. So, um, let's work on another problem. Does anyone have any other problems that they want to take a look at? All right, I guess we can do number one and then number three, and then we're going to look at problems five and four, right? And then if we have time after that, we can look at the last few. But yeah, so for problem three, we're given a 4 by 4 square grid. We ha already have one of those here, so I'm just going to use that. And um, each unit square in this 4 by 4 square grid is colored one of three colors. I'll just label them like red, green, blue. And you're asked to find, over all such colorings, the maximum number of these subtiles that can contain one of each color, right? And so generally for this type of question, we want to look at where this type of tile can appear, right? So where can this type of tile appear? Um, I will answer that question at the very end. Like I will give some tips as to how to write proofs, but right now we're just gonna kind of work on the theory and then the, techniques that you can use to actually solve the questions. Yeah, so I guess you could find these tiles at the corners, but like that's not all the tiles that you could have, right? Like for example, you could have this one right here. So how could you describe all of these L tiles, right? All right, so um the thing I was thinking of is you could take a 2 by 2 subgrid of this grid, and each of those 2 by 2 subgrids has four L tiles, right? So you have this one, this one, and this one, I think. Yeah. So there's one at each corner, right? And so if you look at the entire grid, right, we want to use kind of a global argument because we've already been able to describe all L tiles in terms of those 2 by 2 subgrids. So what we're going to do is, let me first erase all of these. So what we're going to do is we're going to consider the 9 2 by 2 subgrids, right? Does everyone see why there's 9 2 by 2 subgrids? Because like you can choose any one of these three sets of uh two of length 2, and then you can also choose any of these sides of length 2 to form a 2 by 2 subgrid, right? And so what we can do from here is we can notice that each 2 by 2 must contain some color twice, right? And that basically means that at most two of the L tiles that can be put in this 2 by 2 can satisfy the property. Does everyone see why that is? So I'll give an example. Let's say you have this. Notice that in this case, there are two working L tiles, this one and this one, right? So you can like, there's another case, and that would be when the two that are the same color are next to each other. And in this case, you have this one and this one that work. So basically, what we've established is that in each of the 9 2 by 2 subgrids of this 4 by 4 grid, we can have at most two L tiles. And this demonstrates, the idea of looking at it, I guess, somewhat globally in the sense that you want to look at all of the 2 by 2 subgrids because we know that they describe the L tiles very well, and then look at the maximum number of L tiles that can satisfy the property in each of those 2 by 2 subgrids. Does that make sense, everyone? You guys can like say in the chat if you want, like if it's clear or not. All right. So basically, now we've established that the upper bound is 2 times 9 equals 18, right? Now, we're not done with the problem yet because we've proved that the upper bound is 18, but we don't know that 18 is actually achievable, right? And so to achieve 18, what we want to do is make sure that each 2 by 2 subgrid has exactly one color that appears twice and two colors that appear once, because that's our equality case for this two L tiles that satisfies the property, right? And so what we could do is we could do something like this. Whoops. And here it's, I think, pretty easy to verify that each 2 by 2 subgrid satisfies the property that we want. So now that we've constructed a grid that actually has 18, we're done. So generally in these types of, minimization, maximization type grid combo, you need to prove two things. You need to prove a bound that something is maximal or minimal, and then you have to prove that it actually works. So in this case, we proved the bound of 18, and then we showed that 18 actually works, right? And this goes for algebra too, like in inequality sometimes, if you're asked to find minimum or maximum, you have to show a minimum or maximum. And then you also have to find an equality case. So, this technique also appears here in grid combo. Right. So hopefully that was clear. Does anyone have any questions about this? All right. If not, then I guess I'll do the next question. So we're gonna. Okay. So I guess we'll do four actually. Yeah, let's just start with four. So I know this is a huge block of text. Um, while I'm drawing a diagram for this, everyone should read it if you haven't already, so that you can like follow along with my solution. Oh, excuse my horrible drawing skills, but hopefully it's going to be understandable. All right, so this problem presents an entirely different idea compared to the previous two. Um, and that's a general theme in grid combo. A lot of the time, grid combinatorics problems will use a lot of different ideas, so there are a lot of things to try. And often, if you try all of them, you'll probably find one that works. Uh, and in this case, what you want to do is you want to look at what's actually happening, right? You want to analyze the move and what it actually does. So let's, you know, consider. So basically, what a stone move does is it swaps the x or y coordinates of two of these uh, stones if you label the grid with coordinates. So let's say you label it like this. And there's no other way to describe what the process is doing because they literally use coordinates in their problem. So this suggests we're going to be keeping track of coordinates, right? Because often in grid, often in combinatorics problems, we look for something that doesn't change. And something you can notice about this process is it doesn't actually change which x and y coordinate appears, and it doesn't change how many times each x and y coordinate appears. And that's a huge step because knowing that, let's say we like swap these two, we're basically permuting either the x or y values and keeping the other coordinates the same, right? So let's say, like, let's look at the x coordinates of these. So they would be 2, 3, 5, 6, right? And if we look at the y coordinate attached to each of these stones, it's going to be 5, 3, 2, 4. All right, so this is the y and this is the x. But notice that when we swap these two back, we're basically swapping the y coordinates of these two, right? So we're going to swap these. So we're asked to find how many of these, board arrangements cannot be attained from each other. And so that suggests just looking at these, right? These sets of x and y coordinates to determine, the desired answer, right? So first of all, notice that we simply want to place m stones in the, I guess this is a bad grid because it's not n by n, but you know what I mean. So it's a n by n grid. So we want to choose the x coordinates and the y coordinates, right? And so ideally, um, the answer using stars and bars would be n plus n minus 1, choose n minus 1. Does everyone see why that's the case? Because we're just simply distributing the m stones along, the m coordinates here. I know this is not square, but it works the same. So basically, we're distributing the m stones across the n possible x and y coordinates. Right, so this is the expression that we get for that. Now, so this is the answer that we ideally have. Now, we have to check several different things to make sure this is the answer, because as I said previously, in combinatorics problems, sometimes if you want to prove an upper bound, you not only have to prove the upper bound, you have to construct something for the upper bound. This works similarly, except it's no longer some type of upper bound. You counted like the set of possible x and y coordinates, but you have to make sure that, you know, such a set, like two different sets of stones with different x coordinates or different y coordinates or both cannot be attained from each other. And that's pretty easy because we've already shown an invariant in the coordinates. Uh, Another part of the problem is to show that, every set of placements of stones with the same multiset of x and y coordinates can be achieved from each other. And this is also pretty easy if you think about it, because basically what we can do is we can do some type of bubble sort to get from one permutation to another permutation, right? So let's say we want to get from this board arrangement to, I'll like draw a star to where we want the other ones to be. Uh, Something like this, right? Um, so we want to get from these sticks which are representing stones in the current placement to where the stars are, right? And it's pretty easy to check that the multi-sets are the same. But what you can notice is that what we're basically doing is uh, if we look at the x and y coordinates of the desired positions, they're going to be 2, 3, 5, 6. And the corresponding y coordinates will be 5, 4, 2, 3, right? So what you can notice is that we're basically trying to induce some kind of permutation on the y's to change the placements of the stones, right? And this is clearly possible. We can use some type of bubble sort algorithm. Uh, so like you can sort this in increasing order, sort this in increasing order, and then do the exact steps that you use to sort this and the reverse of the steps that you use to sort this, right? Does that make sense? I know this is a little bit, heavy in like ideas, but does everyone understand this? Yeah, yeah. So basically, we're done, right? Because now we've proved that every two placements of stones with either a different multi-set of x coordinates or a different multi-set of y coordinates cannot be achieved from each other. And then we've also proved that, you know, if there's the same set of multi-sets of x and y coordinates, then they can be achieved from each other. But there is one more part. When I said we're done, that's because we kind of neglected a pretty trivial part of the problem, but is important also. You need to prove that each such choice of x and y coordinates must lead to some, arrangement on the board. But that's pretty easy. Just, take the pairs of x and y and put them on the board, right? And so we're done. But the key is to realize that all three of these steps are important. We looked at the coordinates, right, and how they change, and that led to the invariant that we use throughout this problem. But another important takeaway from this is that you need to make sure that you've done everything that you need to. I know that's like a little bit of a hand wavy, advice, but a lot of the time you need to make sure that you don't miss any of the parts. So in this case, right, we needed to prove that I'll just call this like, Evan Chen called this like the signature, so I'll call it the signature, right? The sets of X and Y coordinates. We need to make sure that two arrangements with the same signature can get to each other, and two arrangements without the same signature cannot get to each other. And that came from the invariant and inducing the permutation. But those are both essential to proving that this answer is correct, because to determine this answer, what we did is we used stars and bars to just basically assign the coordinates to each of the endpoints, right? And also that last part about um, actually having an arrangement, that's to make sure that each of these are actually counted in the set of like stone arrangements on the board. So does that kind of make sense? Okay. So someone's asking for how I got the answer, right? And I said this was by stars and bars. Um, I don't know if like it's called that, but you know, it's like when you distribute the m stones across the n possible like x coordinates, right? Oh, maybe I should make this n minus one. Yeah. So when you distribute each of the m stones, what we're basically looking for is an assignment of x and y coordinates, because we've proved using this coordinate invariant type argument that what we're basically trying to do is just randomly assign each of the m stones to some set of x coordinates and some set of y coordinates, right? And so to do that, we can just use stars and bars, right? It's like distributing m candies to n kids, right? We're basically now distributing m stones to n different possible coordinates, and we're doing it again for the y also. So, by stars and bars, this would just be, uh, I think I wrote n, yeah, it's n minus one. Yep. So does this make sense, everyone? I know this was a little bit, heavy on the ideas, and I presented them pretty quickly, but hopefully this all made sense. Does anyone have like any questions about this? Anything to re-explain?
I let's start. Let's move on to a next problem, maybe a bit easier one. This one might be quite hard. It was USAMO people. Okay, not hard, but yeah, USAMO P6 is pretty hard, I assume. Perhaps did we do the problem 3 already?
Yeah, yeah, yeah. The key to that problem was like up here. I drew it up here. But
Okay.
if
No,
you look at that,
oh,
it's
just the coloring argument, yeah.
it's noticing that each, L tile can be very nicely described by a 2 by 2 subgrid, and then just counting those 2 by 2 subgrids.
Okay.
Right. Yeah.
Well, did we do the problem 1? Not.
Yeah, I'll try doing the problem one now. Yeah.
Yeah, yeah. I think that's for the best because like not many people are familiar with the grid combo, in my opinion, but I'm not really sure. So we
Yeah.
should perhaps start with like a bit easier one. I think most of the people found it a bit hard to follow. That's why there was silence. So let's just start with problem 1 and then yeah, we'll continue from there.
Yeah. Um, Please feel free to interrupt me if you're feeling it's a little bit, going a little bit fast. I'm just presenting it in like the most natural way I can, but if you feel like it's not quite understandable, please feel free to tell me. All right, so let's do problem one. So let's go over here. Yeah, so everyone has read the problem, I'm assuming. So we have a square grid with odd side length. It's a horrible square grid. So here I'm drawing a 5 by 5 as a small example. In these types of combinatorics questions, a lot of the time, if you don't immediately realize something, doing small examples is often helpful. So let's say you're given like, you want to prove something for, I don't know, a 2 to the power of 2024 times 2 to the power of 2024 grid, right? Often those big numbers are not very fun to deal with, right? And so what you want to do is you want to look at a small case. So here we're going to look at a 5 by 5 first. And so we know that these are removed. Yeah. So we know that these corner squares and then the center square is also are all going to be removed. And what we wish to do is we wish to pair up the squares into diagonally adjacent squares like this, right? So the first idea here would be to kind of think about how you would categorize such pairs of squares, right? So remember in the problem 3, we categorized the L tiles in a way that was easy to deal with by just using the 2 by 2 squares. And we're going to use somewhat of a similar idea here, where we're going to categorize each of the possible pairs, right? So we're given that we want the diagonally adjacent ones, right? Does anyone notice anything about these sets of two diagonally adjacent squares? I'll draw the other way also. So, like any ideas are fine here. Like, uh, just give me any ideas that you might have as to how to easily categorize these pairs of squares. Yeah, so someone said, huh? Wait,
They're
sorry.
from different rows, like each of the cells. Different rows or different columns, one of the two.
Yeah, yeah, yeah. Yeah, definitely, right? You notice that each pair of squares, they're going to be in different rows. So that motivates looking at, how many different squares are in the odd rows and the even rows, right? Because, you know that each pair of diagonally adjacent squares, they're going to be in different rows, right? So basically that means that, let's say there are A of these here, then there are going to be B of these here, and then they're going to be like C of these here, and then so on, right? So then what you notice is that, uh, the number of these pairs in the first, third, and fifth row is going to be the same as the second and fourth rows, right? Another way to describe this that, is a very commonly seen technique and is used also in problem 6 is you might want to color the board, right? So I will color the board. So basically the squares I'm drawing on right now are going to be colored, right? And so notice that after doing this, right, each pair of squares that we're going to want contains one colored square and one not colored square, right? And so does anyone see how this could motivate a solution, right? How could this, what do we do from here? What type of argument will we do from here?
If we're pairing everything, then like in each pair there's one colored square and one not colored square. So if we're pairing everything, then there must be an equal number of colored and non-colored squares.
Yeah. So that's a great idea, right? So because we know that, we removed the corner squares and then we also removed the center square, or basically in this case, right, we would basically be removing a bunch of squares of the same color, right? And that combined with the observation that was just made about, each pair having one colored and one empty, and hence, there must be the same number of colored and empty squares, means that we can kind of use a bounding argument, right? So in this case, right, let's see. So there's 3, 5, 4, 5, 3, right? So it just happens that there are 10 of these and then 10 of nothing, like 10 blank ones. I guess I'll just draw the blank one, right? But like, if you can kind of imagine a bigger grid, maybe I should draw it out. Right? Let's like, right? So this is the bigger grid. If we cross out the center, the four corners, and then we color the rest, right? I'm not going to color them, but I'm just going to mark the colored rows with arrows. What we can realize is that, let's see. So 5, 7, 7, 6, 7, 7, 5, right? What we can notice is that in this case, there would be 5 plus 7 plus 7 plus 5 colored squares. So that would be 24 of these. And that means that there are 49 minus 24 minus 5. So that would be 20 non-colored squares. So this does not satisfy the property, right? Does everyone see that?
Yeah.
Yeah. So this easily generalizes, right? If we simply look at the parity, well, technically mod 4, but if we look at n mod 4, right? There's two different scenarios. Either all 5 of the removed squares, so the ones with X's on them, are on marked, colored rows, or all 4 of the corner removed squares are on colored rows, but the middle square that's removed is not, right? And so you would have to do a 9 by 9 for this, or like a 5 by 5, like this 5 by 5 shows that. So like in this 5 by 5, you see that the 4 corner squares that are removed, they're on colored rows, but also the middle one. But in this 7 by 7, that's not true, right? The middle one is on a not colored row. And so both of these can be solved by bounding. So what you can realize is that there are n squared minus 5 total unit squares. And you want, well, you want So there would be, well, we're going to let n equals 2k plus 1 to make this easier. But there's going to be k plus 1 of these colored um, rows and k of non-colored rows. Does everyone see why? It's just, kind of looking at it. And then so that means that, we can find a formula very easily from here. What we can do is, k plus 1 colored rows, and then there should be, n in each row, but, it's either -4 or -5, doesn't matter. And then in the non-colored rows, there are kn squares, and then it's either -1 or -0, depending on which case. But you can quickly realize that this term quickly outgrows this term by a lot, and so these constant factors, they're only there to, make n equals 5 constructible. And since we, want to look at small cases, right? And this this motivates that, we also definitely need to look at 3 by 3 to make sure that, that's impossible, or like to make sure that's possible. We're going to look at that. So, right? And so we remove the corners and we remove, oh, my bad. I don't know what that was. Yeah. All right. So this would be, the grid with the corners removed and the center removed, right? And so we can pair up the squares like this. And so that's basically the whole idea of the problem. We want to like color the squares, or you can kind of just notice that the sum of the, squares in these rows must be the same as the sum of the sum of the number of squares in these rows, right? And the bounds that we have for the number of squares, we have to move over here. These bounds motivate, the only such solutions are very small ones, because as n gets big, this grows much faster than, grows faster than this. And yeah, that's basically the entire point of the problem. Does anyone have any questions about that?
I have a question.
Yeah.
Um, like I considered a different coloring, something like a chessboard, and I considered the parity of the number of black squares. Like if you did a chessboard coloring, then two diagonally adjacent squares would be of the same color, right?
Yeah. Yeah.
And like if you consider the parity or like mod 4 for the number of black squares or white squares in that configuration, would you get something similar?
I think so. Yeah. Um, in this like type of chessboard coloring, you have that yeah, you basically have the same thing, right? So in this case, it would be like the 4 remove squares, they're all like empty again. And
Yeah.
then in this case, right, you would have that, whoops, you would have this, maybe I removed the wrong ones. You would have this type of coloring, and actually in this case also you have that the 4 corners and then the center one, they are all empty. They were all empty before you removed them.
Yeah.
And so that would mean that you have n squared. Well, we're going to go back to the n equals 2k plus 1 part. So that
Yeah.
would be the odd rows, so that means that, let's see.
An odd number of blank squares, probably. Wait, that depends on if it's mod 4. Uh,
Yeah.
Wait.
I you would need to work out the details for this. I'm not quite sure, like off the top of my head, if this works. Maybe
Oh,
it does.
there's some casework related to like a mod 4, I think. Like if it's if it's 3 mod 4, then there's an even number of blank squares in the marked rows, and then there like I think it reaches the same thing. Like it's just some verification for the idea. Like it probably
Yeah.
works, right?
I would think so too. I mean, generally, like coloring, like the board, I
Mhm.
think any coloring of the board that's like either checkerboard or like coloring the rows, they should all be considered. For this question, I feel like both would work. You would have to check that though, like you would have to manually calculate like the number and then like verify that they're not the same or the same.
All right, all right.
Yeah, I don't know off the top of my head if this would work. Um, the row, like coloring the rows, like every other row, that
Mm,
argument works because it's like quite motivated by the fact that, you know, they're in different rows, so you want to like count
yeah.
the number of, you know, squares and, you know, even and odd rows to make sure they're the same. But like
Mm,
this type of pattern, I feel like is also pretty common, like checkerboard patterns,
yeah.
um, and is worth a try, I feel like. Yeah,
All right. Thank you.
no problem. Does anyone have any other questions? Yeah, so let's go back to so yeah, so we've basically done the first four problems. Does anyone have any questions about those four? I know number four was a little bit tricky. It's a lot of IDs. It's if you want to write it up, it would be pretty notation heavy, I feel like. Uh, and I went pretty fast. But does anyone have any questions about problem four? Any of the parts that would help to re-explain? Yeah. Yeah. So from here, I feel like, you know, I don't want to spoil all of the problems for you guys. You know, I didn't give you too much time to think about them. So, you know, I feel like the key takeaways that we've had so far are that these problems have a variety of different techniques, right? So I'm gonna like list them out. So first, the first thing is you want to remember your fundamentals. You want to have as many tools in your toolbox as possible, right? And remember that problem on induction. That was a that's a very motivated, you know, type of method to do such a problem because the base case, which would be one pink cell, is quite easy, and the other cases that with more pink cells can be easily, you know, generalized to the cases below them. And, you know, uh, another thing would be to, you know, when you're doing these types of questions, there are a lot of different methods that you can use. So I'll like list some of them. So there's coloring the grid, right? And this was shown in this first problem where we had to color the grid to show that, you know, the number of cells of each color are going to be the same. And then we counted when that's possible. And another technique is to characterize what we're looking for in an easier way. So like remember in problem three, the L tiles are slightly annoying to deal with, right? But what you can notice is that the L tiles, they're all contained within this 2 by 2 that is a little bit easier to look at, right? And so that's what we kind of did, right? So we want to characterize in an easier way. And another thing that we saw is that we want to remember the fundamental combinatorics techniques, right? So like invariance in like problem four, So invariance and monovariance, they may come up in such problems. And, I wish I could say, what exactly you want to look for in a grid combo problem, but there are so many different categories of grid combo problems that it's practically impossible to describe like every possible, grid combo problem that could appear, right? And so what I would generally suggest is trying small cases if, you can't see anything immediately. And also, analyzing the problem, like what doesn't change in like the invariance. And like and for example, in the L tile like problem, like what can I do to simplify what I'm looking for, right? L tiles are annoying, but squares aren't, right? And, I feel like this gets easier with experience. Over time, as you like gain exposure to more types of grid combo problems, you'll find that these types of problems and how to solve them, you kind of start to build an intuition for them. You like see a problem and you're able to kind of see what will work and what doesn't. But that will only come with experience. Um, Hopefully, like what I've like presented today has given you a little bit of intuition as to how to approach these problems, but there are a lot of techniques um, that that I still haven't really talked about, right? And one of those would just be to use an algorithm. Uh, that's like problem 5. Uh, I will give a few pointers on that. I don't want to like fully spoil the problem because like I know I've already like presented a few problems already and I don't want to spoil any more of these good problems. But uh 5, 7, and 8, they're all very algorithm-based problems, and a lot of the time they rely on you trying small cases, being able to, you know, kind of just think about the process that's going on. So, and honestly, this was kind of showcased in the fourth problem, right? We thought about the process of the moves, um, the stone moves, and we realized that there was an algorithm, in that case, like bubble sort or like inducing the permutation. That algorithm would allow every configuration with the same stone move to get to each other, right? And that was kind of an algorithm. And so thinking about the process, what's actually going on, is very helpful in constructing an algorithm. And I know this is very hand wavy, but as I mentioned, in grid combo, there's just too much to describe under one umbrella. So these are just some general tips as to how to approach these types of problems. All right, so these are just some general tips. So like remember your fundamentals, induction, things like that, parity arguments. Those are pretty fundamental things, and often you want to remember those. And this really ties into these techniques. These techniques could be considered fundamental, and a lot of the time when you dive into a problem, like if you have enough experience, one of these techniques or even maybe some other technique will pop out at you, right? And so what I recommend is just kind of looking through more like combinatorics problems. Combinatorics is a heavily experience-based part of math because as you do more and more problems, you kind of gain an intuition as to what works and what doesn't. And so, these problems, if an experienced contestant would not find these extremely challenging because they've already seen very similar ideas in a lot of other problems. And I know that goes with like all of math, but especially for combinatorics, an idea can just jump out at you if you've seen that idea enough, right? And so I recommend just going through a bunch of problems. Like if you want, I could give you more problems outside of this problem set, but it's very useful to kind of just look through a bunch of combinatorics problems, maybe even like specifically grid combo problems to like kind of gain more intuition as to how these are approached, right? There's and combinatorics is one of those, subjects where there's no magic pill to like solve every problem. There's no theorems that are extremely powerful as to break apart the problem. A lot of the time, you literally have to try what the problem is saying, right? And, that's very important in grid combo too. And so hopefully, these tips like provide you a little bit of intuition as to how to approach these types of problems. And yeah, I mean, I suggest everyone go try the problems that I didn't get to cover today. So like 5, 6, 7, and 8. They are pretty hard, I would say, but using these techniques, you could probably solve all of them, right? So just take a few, I don't know, a few hours to look through these problems, give an honest attempt to them, and I could give you hints if you would like. Just DM me on Discord, and we'll do that. So yeah, that's gonna be that for today. If any of you would like to stick around, uh, and ask me any more questions, it doesn't have to be grid combo. It could be like other types of combo, other subjects. That would also be fine. Yeah, but that's all for today.
All right, thank you.
No problem.
Yeah, I think that's it. Thank you so much, signing for doing this.
No problem. No problem. It was very interesting, getting to talk
Zone,
about.
do you want to ask anything? Did you want to? I don't
If
think.
anyone has any questions, I can answer to the best of my ability.
Mm-hmm. Yep, I think okay, P2. Well, P2. P2 of what?
So this P2, like the pink cell one, yeah. So that question, it's more of, again, it's like sort of like a algorithm and maybe not. It's, it's fundamental in the sense that you're using an induction to construct such a tiling. So I'm just gonna quickly draw the grid again. Uh, whenever whenever you do these, the small case will help, right? And so the small case here would just be like one pink cell here. I'm just going to use black to color it again. And in this case, you can just take the whole grid, right? It's pretty obvious. But like what happens if there are more than one pink cell, right? Let's say there are these, right? And something you could kind of motivate with this is like you can divide the grid based on where these pink cells appear, right? Using these vertical lines. And then you can further subdivide these if needed, right? That's an argument. And to formalize this, you could kind of use an induction. It's like what you could say is take in the base case is equal to 1, you just color the whole grid. And if you have more than one, what you could do is you could divide the grid in half using, not necessarily in half, but divide the grid using some vertical bar like this. And then you have two smaller cases with So in this case, there would be 2 pink cells, and this is 1 pink cell. And, if we do an induction, these are going to be, the smaller cases. So by inductive hypothesis, we're going to be done, right? Something to notice though is this only works, I guess, if they're not all in the same like row like this. Uh, but in like this case, you could kind of just divide it in half like that, and it would work. So, or you could just explicitly construct an algorithm where you just kind of divide it in like divide it vertically over and over until there's like groups like this. Um, and then subdivide them further, which is kind of what I was trying to get at uh, during my presentation. But I mean, the induction is kind of like a more rigorous version of this in a sense because you're continuously dividing it in a way that works. And this is just a more wavy way of saying that. Uh, did that answer? Is that like more understandable?
So while we are dividing those already divided squares, sometimes they may not be along the border.
Um, Wait, could you repeat the question?
For example, if it were a 5 by 5 square and the middle 9 were colored, it wouldn't be possible, would it? Since the divided squares would not be along the border.
Ah, I see what you mean. So in that case, right, this algorithm, you know, again, it's like you want to analyze the process and look for an algorithm, right? In this case, it would be. And if we color the middle 9 squares, give me a second to draw the diagram, right? So these 9 squares in the middle, if you divide it in like half like this, right? Not exactly 1/2, but like you divide it into 2 sections. Um, then by inductive hypothesis, this would work because like in this case, right, what we could do is you divide this in half and this in half, right? And then you divide each of those regions in half. Well, this one you don't divide because there's already one. And when I'm saying like 1/2, it's not actually 1/2. It's just drawing some vertical or horizontal line to break the rectangular square into into two smaller rectangles or squares, such that each of them has at least one pink cell, right? And then we can continue doing that until each one has exactly one pink cell. So, first we drew this one, and then we drew this one, and this one, and then we drew this one, and this one, and this one. And then finally, we can draw this one and this one, right? You see how that works? So now this is one of them, 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 right? So this would work. And like basically the way I explained it with like an explicit algorithm would just be to divide like into regions like this and then subdivide each of these. So it would just be that. It gives the same construction, but the induction gives like a more formal way to do that. Does that answer your question?
Yes, thank you.
Yeah, no problem. Any other questions?